In the first video we explained why we need to change the way river biodiversity is monitored in England. If you haven't watched it yet, you can find a link to the video below. To summarize, we said there are 3 problems with the way river biodiversity is monitored today. Let's look at how each of those problems can be solved, or at least mitigated. Imperfect detection refers to the tendency for biodiversity monitoring techniques to miss species inhabiting rivers. All techniques are imperfect, but some miss more species than others. To monitor river biodiversity most effectively, we should use techniques that miss the fewest species. Our recent research has shown that commonly used monitoring techniques fail to detect more than 50% of species estimated to be present in the habitat at the time of sampling. In some cases, more than 80% of species are missed. Fortunately, we now have better alternatives to the conventional techniques that are used to monitor river biodiversity in England today. One technique known as DNA metabarcoding has been consistently shown by research to detect more animal species than conventional techniques. DNA metabarcoding identifies organisms collected from the river by looking for strands of DNA that are unique to each species. This allows us to tell which species an organism belongs to, even when that organism would be too difficult to identify by eye because it is damaged, too small, or just missed by chance. DNA metabarcoding can also be used on water samples to identify species living in the river, just from the DNA they leave behind. We call this environmental DNA, or eDNA metabarcoding, and it is a good alternative for fish and other larger animals, because it doesn't involve taking any living organisms back to the lab. Other new technologies that use artificial intelligence to identify species from images of individual microscopic organisms are also promising alternatives, and may help to reduce the cost of monitoring by speeding up the process of identifying organisms compared to conventional techniques. Even with more efficient techniques, we cannot be sure of identifying every organism, so it's essential that we use sound sampling design and statistics to help us account for the fact that our monitoring is imperfect. To make the best use of new monitoring techniques and statistics, we need to change the way we collect organisms from rivers. As an example of why this is necessary, let's look at how invertebrates are collected from rivers. The conventional monitoring technique for invertebrates involves collecting organisms like fly larvae and snails by kicking the riverbed and catching the things that are dislodged into a small net. All of the collected organisms and debris are combined into a single container that is taken back to the lab for identification under the microscope. Because we only get a single sample of organisms from an unquantified area of the riverbed, we cannot say how many individuals of each species live in a given area of the river. This conventional way of collecting invertebrates also limits the amount of information we have to estimate the probability that a species was missed or incorrectly identified. To improve the quality of the information we get from monitoring, we need to do 3 things: collect organisms from a fixed area of the river, repeat this several times covering all areas representative of the river habitat, and take each repeat sample back to the lab in a separate container for identification. This would work slightly differently for other groups of plants and animals. For example, if we are using eDNA metabarcoding to monitor fish, then we would need to collect several repeat samples of a fixed volume of water. By giving us data on the number of individuals belonging to each species living in a fixed area of the river, this new technique would allow us to use statistics to estimate the probability that a species was present in the river, and how its population size compares to other rivers or the same river at a different time. Not only that, but statistics can tell us how sure we can be about the accuracy of this information. Under the present framework for assessing the ecological status of rivers in England, historical data are used as a benchmark for rivers today. To be considered good, a river must have similar species to equivalent rivers in the past. Most of the historical data used were collected in the 1980s, from rivers thought to be minimally impacted by human activities at the time. However, climate change has caused significant shifts in English river environments over the last 40 years. For example, average water temperatures have increased by an estimated 0.3 degrees per decade, river flows in most places have increased in winter and decreased in summer, and extreme floods and droughts have become more frequent. Temperature and flow are 2 of the most important factors influencing the presence and abundance of freshwater species, so these environmental changes have altered the biodiversity of our rivers. A good river today is therefore unlikely to have the same species as a similar good river in the past. At the same time as climate change has been altering river biodiversity, concerns about water quality have shifted from nutrient pollution to a wider range of emerging pollutants. These include surfactants, pharmaceuticals and biocides. Urban areas have expanded, and agricultural practices have changed. We are taking more water from rivers for use in farming and industry. Several invasive species have also rapidly expanded their populations. The effects of these non-climatic changes on freshwater biodiversity are known to be masked by climate change, and this masking effect is expected to increase in the future. In other words, climate change means the past is an increasingly poor guide to today. To secure our ability to protect rivers against chemical pollution, water abstraction, species invasions, and other human impacts, we must move away from using historical data as a benchmark for rivers today. We can do this by using more of the information available to us when interpreting new monitoring data from a river. Instead of looking back in time, we can use machine learning to tell us what the river's biodiversity would be like in the absence of the impacts we're interested in. For example, which species would we expect to see if the river had better water quality, or if we eradicated a certain invasive species? What if we took less water from the river, or removed modifications like weirs and concrete banks? We now have the data and machine learning techniques available to answer these questions, and our research has begun to show how this new way of benchmarking rivers can work by accounting for imperfect species detection. The added benefit of this approach is that it can not only give us a benchmark against which to measure a river's status, it can also tell us what we need to do to restore biodiversity. Which leads us to the third and final problem. Our reasons for monitoring freshwater biodiversity have changed in recent years. The original purpose of monitoring was to infer water quality by looking at the organisms inhabiting rivers, but we are now interested in monitoring biodiversity for its own sake. This is a subtle yet important change because it affects the choices we make when monitoring rivers. For example, if we're interested in inferring water quality, we might be happy to record broad groups of species living in the river, such as the abundance of certain families of mayflies or freshwater shrimps. However, there are now legally binding targets to halt and reverse the loss of species. We therefore need to record which particular species each organism belongs to. If we are to achieve freshwater biodiversity goals, we need to make much better use of existing data, adopt new, more efficient survey techniques, account for imperfect species detection, and develop predictive machine learning models to help us decide when, where, and how to intervene to protect and restore species populations. To learn more about how to address the problems with river biodiversity monitoring, follow the link to our policy brief.